The following video is on optimization. Let's look at an example. A farmer has 700 feet of fencing and wishes to build a rectangular enclosure split into half by the fencing. What dimensions will maximize the enclosed area of the pens? So the first step with these optimization problems, as always, is to draw a picture. So here's my pen split into half. Notice that if I made some guesses at the lengths of each of the sides of the pens, I could guess that the long ends are each 200 feet and the short ends are each 25 feet. In this case, I would get each pen having a dimension of 1,000 square feet. But I could also do this another way. What if I made each length 100 feet? Then I could see that the dimension of a pen would be 20,000 square feet. Finally, what if I looked at each pen having the long side being 220 feet and the short side being 10 feet? So then I could see that I have a total enclosed area of 4,400 square feet. So notice that depending on what dimensions I look at, the size of the enclosed area changes. So what we want to do is try to maximize the enclosed area of the pens. So how can we find the largest area that we can enclose? To start this problem, I'm going to label the sides of my pen with X's on the short sides and Y on the long sides. These may not be the long sides or short sides when we're actually finished, it's just on the picture this is how I drew it. Now I know that I have 700 feet of fencing, so that means that summing up each of the X's and Y's, I should come up with 700 feet. So 700 equals 4x plus 3y. The thing that I want to maximize is the area. So I have two pens, and each of the pens have dimension x times y. So the area that I'm trying to maximize is 2xy. I want to find the absolute max of capital A. In other words, I want to find what is the largest value of A that we can find. In order to do this, however, we'd like to take a derivative, but we currently have too many variables floating around here. We have an A, an X, and a Y. So how am I going to get rid of one of my two variables? Well, remember I have the function up above, 700 equals 4x plus 3y. So what I'll do is solve for one of those two variables, in this case y, and plug it in for y in the area function. So the area is equal to 2x times 700 minus 4x over 3. When I simplify this, I get negative 1400x minus 8x squared all over 3. Now I can take the derivative because the area is written entirely in terms of one variable. So I get 1400 over 3 minus 16x over 3, which is the same thing as saying 1400 minus 16x over 3. Now we want to find the critical values. So when I do that, I see that it's equal to 0 when 1400 minus 16x equals 0, or in other words, when x is 87.5 feet. And notice that it will always exist. Furthermore, we now need to check that this x value that we just found really does give us a maximal area. So I check it on the number line by plugging in values less than and greater than x into my derivative. If I plug in 0 into the derivative, I end up with 1400 over 3, which is positive. If I plug in 1,000,000 in for x, I end up with a huge negative number over 3, which is negative. So that means that I really do have a maximum at x equals 87.5. That means that the area is maximized when x equals 87.5 feet. Unfortunately, we're not done yet. We still have to find y. But in order to find y, remember that y equaled 700 minus 4x all over 3. So I'm just going to plug in x equals 87.5 into that formula for y and solve for y. I end up with y equals 116.66666666 feet. And now I know that the area is maximized when x equals 87.5 feet and when y equals 116.66666666 feet. This is the format of a typical optimization problem. Notice that we started with drawing a picture, labeling the picture, and then we came up with two different equations. One of the equations was the one we wanted to optimize. In this case, we wanted to maximize it. That's the function we end up taking the derivative of. The other equation is only used to get rid of variables. Once we've gotten our optimized function down to one variable, we then take the derivative to find relative maximums and minimums. We use the number line to test for what a max or a min is, and then solve for the other variable. Let's look at another example. A box is to be made from a 100 centimeter by 100 centimeter piece of cardboard by removing squares from each of the corners and folding up the sides. What dimension should the squares be in order to maximize the volume of the box? So the first step is to draw a picture. Here we see our square shape of cardboard. Notice that it's measured 100 centimeters by 100 centimeters, and we are cutting squares of length s by s from each of the four corners. We'd like to maximize the volume of the box that's formed when we cut out these corner squares and fold up the sides. Notice that the inside lengths will be 100 minus 2s and 100 minus 2s. So we want to maximize the volume of this box, which notice the volume will be the area of the base, which is 100 minus 2s squared, times the height, which will be s. This is our formula that we want to optimize, so the next step is to find the critical values. When we take the derivative of v with respect to s, we end up with 12s squared minus 800s plus 1000. So we find the critical values by setting it equal to 0. This will happen when s equals 800 plus or minus the square root of 640,000 minus 4 times 12 times 1000 divided by 2 times 12. Notice I got this using the quadratic formula. This simplifies down to s equals 100 plus or minus 5 times the square root of 370 over 3, which is approximately 1.27 or 65.39. When we plug these values onto the number line for v and plug in values in each interval, we see that any number less than 1.27 will be positive, any number between 1.27 and 65.39 will be negative, and any number greater than 65.39 will be positive. That means that I have a relative maximum when x equals 1.27. And remember, we want to maximize the volume. This means that we want v to be maximized, so we want s to be 1.27 centimeters. Let's look at another problem. A farmer wants to build a rectangular enclosure for her cattle. The pen will be divided into half using wire fencing, but the outside of the fence will be made out of wood. Wire fencing costs $10 per foot, and wood fencing costs $30 per foot. We want to know what dimensions will minimize the cost if the farmer needs each pen to be 800 square feet. Notice that this is slightly different from the first problem that we saw, because here we want to minimize the cost for building the pen as opposed to maximizing the area. In this case, the area of each pen needs to be 800 square feet. Let's start by drawing a picture and labeling it. Notice that the blue border is the wood fencing and the red border is the wire fencing. So that means that we are going to need, well, first of all, the area of each pen is going to be 800 square feet, so 800 needs to equal x times y. And the amount of wood fencing that we're going to need is going to be 2x plus 4y, and the amount of wire fencing we're going to need is just x. So that means that the cost to build the entire enclosure will be $30 times the amount of wood plus $10 times the amount of fencing. So in other words, our cost is going to be $30 times the wood, $10 times the wire, added together to get the whole cost. Now here we have two variables, so we're going to use the 800 equals x times y to get rid of one of our variables. I decided to get rid of y. So that means that the cost is going to equal 30 times 4 times 800 over x plus 2x plus 10x. This simplifies to 96,000 over x plus 60x plus 10x, or 96,000 over x plus 70x. Now we want to find the relative max for C. And in order to do that, I take the derivative, find the critical values. So notice that the derivative of C is going to equal 0 when x equals plus or minus 37.03, and it does not exist when x equals 0. Notice that we can actually ignore the negative 37.03 value because we don't want x, which is supposed to represent a length, to be negative. Furthermore, we can eliminate 0 because we don't want our length of the pen to be 0. Even still, we can play the number line game and we can find maxes and mins, and thankfully we see that the only critical number we wanted to consider is indeed a relative min. We have a relative min when x equals 37.03, so that means that the cost is minimized when x equals 37.03 feet. We still need to find y, however, but notice that y equals 800 over x. So plugging in x equals 37.03 feet, we get y equals 21.6 feet. So therefore, the area of each pen is maintained to be 800 square feet, and the cost is minimized when we have each pen with dimensions 37.03 feet and 21.6 feet.